Hello, I'm John Manura. This video will be the first video of a planned 5-part video series on the design, production, and testing of this fully automated or CNC Rose Ornamental Lathe. The Ornamental Rose machine is used to design unique patterns in both the faces and the sides of cylindrical shaped objects. In this first video in this series, I'll be briefly describing this fully automated Rose Ornamental Lathe. I'll then briefly describe the various components that I developed for the system. I'll briefly describe the software that I developed to operate the system, and then I'll show examples of some of the finished projects made with this system. This automated Rose machine is continually being developed, and there will be many changes made in the future as I continue to come up with new ideas and new designs and new software improvements to the system. There will be 5 introductory videos in this video series on the automated Rose Ornamental Lathe, which are as follows. Part 1 will introduce the new automated Rose Ornamental Lathe. Part 2 will describe the design and construction of the spindle head. Part 3 will describe the construction of the table with the linear rails. Part 4 will describe the electronics console, and Part 5 will describe the software development. Over the next 2 years, I plan on producing a number of additional videos on this project. The Ornamental Rose engine design that I produce is based on the MDF Rose engine design developed by John McGill. However, I made a number of design changes to the spindle head to improve the system and also to make it more stable, and also to expand its capabilities. Several years ago I purchased the main components to produce a Rose machine, and now I'm finally getting around to producing my own Rose Ornamental Lathe. If anyone else is interested in producing one of these Rose Ornamental Lathes, I highly recommend you purchase one of the kits available which contain the main components to build the Rose Ornamental Lathe. These kits are currently available from Collin Tools, and I'll put a reference contact information to this company in the description section of this video. My first goal is to fully automate the CNC Rose machine. The original system by John McGill was a manual system, and I wanted to convert this to a fully automated CNC system using stepper motors to control the spindle operation as well as the movement of the tools. I do have some experience in the CNC automation of several wood and metalworking tools in my shop. I did several YouTube videos on the production of these CNC or automated systems. Let me review these 2 tools in some detail. So what I learned in development and testing of these 2 automated CNC systems will be very beneficial in the design and development of this new automated Rose machine. This is the first system I converted for CNC operation. This was a manual mill I bought from Precision Matthews, and I converted this for CNC operation by adding 4 servo motors, one for the X, the Y, and the Z axis, and a 4th servo motor for the spindle operation. For the operation of the system, I use off-the-shelf software from Centroid Acorn to operate the system. I did design and build the electronic system to control the operation of the system. I've used the CNC converted mill for the manufacture of many parts for my Accu-Slice system, and I'll be using it extensively for the design and production of parts for this new automated Rose machine. I use off-the-shelf software to control the operation of the system, but I design and build the electronics console for the operation. You have a variety of servo drivers for the 4 servo motors, and then electronics to control these systems. This is my automated Accu-Slice system that I developed for the automation of my Accu-Slice system for my bandsaw. This is a more extensive CNC development project. I use a variety of stepper motors to control the X movement as well as the Y movement of the board through the bandsaw blade. I designed the electronic system, including a touchscreen display panel, and I also wrote the software using Arduino programming to control the actual operation of the system. I did videos on both these instrument developments, and I'll put reference to these 2 video series in the description section of this video. What I learned in the development of this automated Accu-Slice system will be very beneficial for my new automated Rose machine, and I'll incorporate many of these same features, including the touchscreen display panel and the pause and reset buttons for this new system. My plan is to use most of the same technology that I used for the automated Accu-Slice system to develop this new automated Rose Ornamental Lathe. I'll be using 4 stepper motors. One will be for the spindle operation, and the other stepper motors will be for the movement of the tooling systems. These stepper motors will be closed loop stepper motors because they're more accurate than the standard open loop stepper motors. My second major goal in the design of this new automated Rose machine was to make the system more accurate and more stable. The original design was made out of MDF. And I made a prototype here using MDF. And I did design this using the Fusion 360 software. And I drew all my drawings up in the system, got all my dimensions set up that I could machine this very accurately. But instead of using flat joints, I made these dados and pins that joins everything together and makes everything assemble much more accurately. So I did make this first prototype out of MDF. Made a couple of other blocks out of this to get my dimensions for where I'm going to put my stepper motors and other mounting systems. And got everything machined and actually assembled a system that was all set to take this to do my next step, which is to make an aluminum system. But I want to do all my testing on the MDF because the aluminum is quite a bit more expensive. The original design used a pivot point to rotate this carriage back and forth. And this may work for something very light such as the MDF, but when I made an aluminum system I needed something a little more stable, more accurate. So I'll be using pillar blocks and shafts to control all the movement of the system. So I have a set of pillar blocks on the base to control the movement back and forth, and a set of bearing blocks up top to control the movement of my shaft. So I machined my first prototype out of aluminum, and this was out of 3/4 inch thick aluminum, and it's pretty big and pretty heavy. And after making this first prototype, I thought I should make it a little bit lighter. So I went about redesigning the system again to make it a little bit smaller, a little bit lighter. Instead of using the pillar blocks, I'll be using machine blocks with mounts in here for the bearings, and I can put the bearings right in here and mount them directly in. Eliminates the heavier pillar blocks. And I also made out some thinner aluminum, and I made the system an inch shorter, an inch narrower, an inch narrower this way, so it's quite a bit smaller. All of these design changes reduced the weight of this entire head assembly by more than half the weight of the previous prototype. This is the finished and assembled spindle head assembly with the stepper motor installed and ready to assemble into the system. So I installed my spindle head into the system, mounted on my table, and I did add 2 plastic sides to the spindle head to again cover up the interior so this doesn't get inside that stepper motor. And the one major change I made was my shaft for the spindle head has a flat end. The original design by John McGill had a 1 inch by 8 thread per inch threaded end that was used to attach a chuck. However, the chucks I use are for my Automated lathe, which is a 1 1/4 by 8 threads per inch, so it wouldn't fit on that existing shaft. So I made a shaft that can be more versatile, and it's just a straight end flat shaft. Then I can make various adapters, such as this adapter which adapts to my standard Automated chucks, which is again a 1 1/4 by 8 thread per inch. But I could have other adapters for the 1 inch by 8 thread per inch chucks. But also this gives me some other options, such as a flat plate, such as this, which is nothing more than a flat plate with a 3/4 inch diameter hole in the center, which again mounts on this shaft and is held in place with some set screws. I embedded magnets into this plate to enable index cards to be attached, and then I use this flat plate for the printing of the rosette pattern. The other option is to use something like this, which is like a flat plate chuck. Again, using that same 3/4 inch diameter hole, which mounts on my shaft. Then I can use double-sided tape to hold my board on there to do my my cutting. Double-sided tape is plenty strong for holding this, since there's not a lot of force being applied with the cutting tools I'm using. And of course, the other option is just to mount the board I'm cutting to a piece of MDF and clamp that in my chuck, or I could clamp the board directly into the chuck. So again, this flat plate shaft gives me a little more versatility over the system. One of the future ideas I have is to make this shaft hollow, so that I can create a vacuum chuck. It'd be nice to be able to hold systems in place with a vacuum. Particularly if I was going to this would be nice if I was doing some machining on my segmented eggs, where I could mount the egg on there, hold it in place with a vacuum chuck, and then do some machining using the ornamental lathe. So very versatile. So again, it just mounts on the shaft like this, and it's held in place with set screws. As I begin to develop this automated Rose machine, I'll be making a lot of changes, and I'll be continuing to redesign and improve its performance. I'm quite fortunate that I have a machine shop with a CNC mill and a CNC lathe, as well as several 3D printers to produce and test some of the design ideas and improvements that I come up with. I do not plan on commercializing this system, therefore I'll make any of my drawings and software available at no charge to anyone who wishes this information. If anyone has any suggestions for improvements to design or additional accessories, please give me a call or drop me an email. I would appreciate any of your comments and suggestions. Okay, next I'll briefly describe the components of the system. Starting with the spindle head assembly, which I described previously. Again, with the plastic sides, I got my wheel with a geared system, and it's a 4-to-1 ratio between my two gears for the system. So stepper motors, moves 4 revolutions for every revolution of the spindle. I have my pivot point to control where it moves back and forth. My chuck assembly mounted on the end of my spindle. I created a dust system, and I 3D printed these dust shields for the system, which collects most of the dust. And I'm using a 4-inch hose here, which actually mounts to a 6-inch duct system, which pumps 400 CFM of air through the system. So it does a pretty good job of collecting the sawdust as it's generated from the system. My linear rails, I have 2 linear rails for the Z position, again with closed loop stepper motors on both of them, and they're synchronized that they run simultaneously and accurately at the same speed. Another linear rail for the X direction, and I have my chuck or my plate here with my AXA tool post mounted, and I made a variety of tool post holders to hold my various tooling systems. My main tool I'm using right now is just a ram rotary system, but I'll be making some other systems in the future. I also made another system top right with the Dremel tool, again with the same sort of mounting plate. Again, it was 3D printed in this case, but in this system I actually machined one out of aluminum. All the electronics are located in a separate metal cabinet under the console. The electronics assembly consists of 4 stepper motor controllers for the 4 stepper motors, the Arduino computer board, 2 24-volt power supplies, 2 5-volt voltage regulators for the Arduino board and Next-Gen display panel, a cooling exhaust fan, and a terminal strip board. I left enough room in the system to add a 5th stepper motor in the future that might be used for either phasing or pumping of the system. The other major component is this display panel. This is a Next-Gen touchpad display panel that I can use to program the system and to operate the system, so that works out quite nicely. And I have both a reset and a pause button. So if the system was running and I saw a problem, I could pause it, correct the problem, and then restart it to continue right where I left off. Or I could reset it and start from the beginning. So those are nice features to have in a system. Again, not for safety and just for managing the system better. The heart of the system is this Next-Gen display panel. And it has the touchscreen display panel. And for the software system, I am using the Arduino software board and software to design the system, and right now I have 17 subprograms to do the various operations. The system is designed with one main program for the overall operation of the system, and this first screen is the main control panel. I have systems for the manual control of the spindle motor. In other words, I can run the spindle motor separately by itself, manually, and I can also control the XY position of the linear rails. Again, I can just do this by saying what direction I want my spindle to move, left, right, or up or down, and that moves it back and forth. Likewise with the spindle, I can jog the spindle, I can run it continuously, I can set the speed, and it runs continuously. I can also do some indexing. I can say if I wanted to rotate it by 15 degrees, I can index it to a certain position and then rotate it to that position. So quite versatile in the way it operates. Then I have various programs. Programs to control the cutting of both the face and the sides of the system. And I'll be going through this in detail in a future video. But it's a very versatile system with a lot of capabilities. In fact, this is the program I just finished for doing cross-hatching on the side of a piece. And you manually put in the parameters for what you want to run, and then you set those parameters, and then you actually start and run it. The system, I probably spent a month designing the overall spindle assembly, but I spent the last 2.5 months just working on software. So I spent a lot more time doing software than the actual design of the system. This is an example of a test project that I just completed using this Automated Rose Ornamental Lathe. This project consisted of generating a crosshatch pattern on the sides of a Paduk wood round cylinder block, and then a rosette pattern on the face of the wood block. I actually ran 4 different design programs for this project. So let me quickly go through the steps of generating this project to demonstrate how the automated Rose machine actually operates. I edited and sped up this video quite a bit to reduce your viewing time. The total processing time for cutting a single depth pass for this project was just under 50 minutes. However, I made 2 different depth cuts for this project in order to produce a deeper and more visible cut patterns, and this doubled the time to produce this project. This is the first program that I used. This program was designed to true up the outer surfaces of a cylinder so that it is perfectly round. I then use a flat tip cutting tool to cut and true up the surface of the board as it is rotated. For this operation, I normally use a fairly fast spindle rotation, but a relatively slow linear travel of the cutting tool. Often a project may be turned on another lathe and then transferred to the ornamental lathe to generate the ornaments. In doing so, the turn piece may not be perfectly centered due to variations in the mounting of the board and the chuck on the ornamental lathe. This retruing or returning of the OD of the cylinder corrects for this error. I normally repeat this cutting step multiple times, slicing off about 5/1000 of an inch with each pass of the tool until all imperfections have been removed. For this next operation, I wanted to generate a crosshatch or a checkered pattern on the side of the wood block. From this screen, I entered the parameters that would generate the pattern I required. This program is quite versatile with the starting and ending position, the number of divisions or segments to create the required angle of the diagonal lines, the quantity of diagonal lines, the feed rates for the spindle as well as the x-axis, and the number and depths of cuts required. I also decided whether I wanted or did not want a top and bottom ring. The program starts by cutting straight circles at the top and bottom dimensions of the pattern. The slicing of the diagonal lines then starts. The rotational speed of the spindle has been accurately calculated to coordinate with the z-axis speed of the cutting tool to give the correct pattern. The pattern is repeated until all the diagonal lanes of the pattern have been created. The design of the software for this program seemed like it should have been quite easy to do, but there were a lot of variables that needed to be included in the calculation of the speeds and feeds. I actually spent 3 full days designing and tweaking the software until it was perfect. And here the pattern is complete. If deeper cuts were needed, the pattern can be repeated with a deeper cutter setting for the cutter. And here's the finished crosshatch pattern with perfect alignment and spacing of all the lines. Once again, I wanted to true up the face of the wood block so that it was perfectly flat with the axis of rotation. This program operates much like the first program shown previously to enable the smoothing and truing up of the face of the block using a flat tip cutting tool. Next, I want to create a rosette pattern on the face of the wood block. Again, this program for creating these patterns is quite versatile. Up to 5 different patterns can be input into the screen to process all of them at the same time. The distance entered is from the center of the cylinder, but you have the option of cutting from the front or from the back of the center position to create different patterns. The total depths and depth increments are also entered on the screen, as well as the speed of the spindle. I'm using a pointed cutting tool for this operation. As the spindle is rotated, the spindle head is rocked against the rosette, which enables the generation of the patterns on the faces of the block. Since I entered multiple depth cuts for this pattern, the cutting is repeated multiple times, moving the cutting tool in after each completed rotation of the spindle. This process is repeated for each of the pattern dimensions that were entered into the previous setup screen. I'm using the same rosette pattern for all 5 pattern cuts for this project, but I could have paused the system and changed out the rosette for a different pattern, or I could also have manually changed the phase of the rosette to give additional unique patterns on the face of the board. The use of multiple rosette patterns, changing the phasing of the rosette, and the cutting on the front or back side of the block's center position provides for an unlimited diversity of patterns and designs that can be produced on the Rose Ornamental Lathe. And here's the finished project with a cross-hatch pattern on the sides of the block and a rosette pattern on the face of the block. I did sand this piece with a floppy disk sander to remove the fuzzies from the cutting process. This concludes this Part 1 introduction to the new Automated Rose Ornamental Lathe. In Part 2 of this video series, I'll be describing the design and construction of the spindle head assembly. In Part 3 of this video series, I'll be describing the construction of the cabinet and the linear rail system components. And in Part 4 of this video series, I'll be describing the electronics console, and in Part 5, I'll be describing the software development. Additional future videos are also planned on the operation of the Automated Rose Ornamental Lathe, along with anticipated hardware improvements and new software programs that will be developed. If you have any questions or comments on this video, please leave your comments in the comment section of this video or drop me an email. And thank you for watching this video.